welcome to this problem walkthrough. Today, we will dive into a unique challenge titled "You have reached a problem that is not explicitly stored in my training data." While the metadata for this problem is sparse, we'll explore systematic approaches to handle ambiguity, analyze potential solutions, and derive key insights. Let's get started. In this problem, you're tasked with solving a challenge that deliberately leaves some ambiguity, encouraging you to rely on your problem-solving skills. The main objective is to determine whether a given integer, n, is even or odd, and return the result as a string. The input to the problem is a single integer n, which falls within the range from 1 to 10,000. The output, in turn, is a string that explicitly states whether the number is even or odd. By adhering to this format, your solution should successfully operate within the provided constraints. For example, if the input provided is the number 4, your solution should output the string even. This is because 4 is an even number, and the output must reflect that classification. On the other hand, if the input is the number 7, the output should be odd. Here, 7 is an odd number, and the output needs to clearly indicate this fact. These examples illustrate the expected behavior of your solution when processing both even and odd numbers. Another example is when the input is the maximum allowable value, 10,000. Since 10,000 is an even number, the output should be the string even. The problem also specifies some important constraints to consider. The input n will always be an integer within the range of 1 to 10,000, and your output must be strictly either even or odd, with no additional formatting or punctuation. Additionally, your solution needs to determine the result in constant time, meaning in O(1) time complexity. To ensure your solution is robust, let's consider a few edge cases. When the input n is at its minimum value of 1, the output should be odd, as 1 is an odd number. Similarly, for the maximum value of 10,000, the output must be even. If you encounter a random odd number like 9,999, your solution should return odd, while a random even number like 42 should return even. By covering these scenarios, you can confirm that your implementation is both accurate and efficient. When we encounter a problem that is not explicitly defined, our first step is to adopt a systematic approach to handle its inherent ambiguity. One option is the brute force approach, where we explore all possible interpretations of the problem. The intuition here is to start broadly, analyzing various scenarios or edge cases that might align with the title or any implied context. For example, if we suspect the problem involves structures like arrays, strings, or graphs, we can test simple operations such as searching, sorting, or traversing. This gives us a baseline understanding of potential problem structures. However, this method is highly exhaustive, with a complexity that can easily reach factorial levels, making it impractical for larger-scale problems. While brute force ensures comprehensive coverage, it is inefficient and unlikely to be suitable for competitive programming scenarios. A more refined approach is to leverage pattern recognition, or what we might call a heuristic approach. This involves interpreting the title to discern potential clues about the problem's nature. For instance, does the title suggest recursion, dynamic programming, or perhaps mathematical reasoning? By analyzing common patterns in similar problems, we can develop heuristics that guide us toward a solution. This method is significantly faster than brute force, often operating within complexities like O(n squared) or O(n log n), depending on the heuristic used. However, it comes with trade-offs. Heuristic approaches rely heavily on assumptions, which means that if the problem deviates from familiar patterns, the solution may be incorrect. Another option is algorithm design from first principles, where we focus on core problem-solving techniques. Here, the goal is to reduce the problem into smaller, testable subproblems or convert it into a well-known problem type. For example, optimization tasks might point us toward greedy algorithms or dynamic programming, while search problems could involve binary search or graph algorithms. This strategy typically balances structure and adaptability, though it requires careful validation to ensure alignment with the intended problem. Among the approaches discussed, the most effective strategy for this ambiguous problem is algorithm design from first principles. This approach offers both structure and flexibility, enabling us to iteratively derive a solution even without explicit details. By breaking the problem into smaller components, we can test our assumptions and refine the solution step by step. The title itself hints at a meta-problem, suggesting that reasoning about problem solving might be central to the task. This makes a systematic, adaptable framework like this particularly well suited. Brute force, though comprehensive, is far too inefficient for competitive contexts. Meanwhile, the heuristic approach, while faster, risks misinterpretation due to its reliance on pattern recognition. Algorithm design from first principles stands out because it balances correctness with adaptability. While it does require more upfront effort to design and validate, this investment pays off in terms of robustness and scalability. Ultimately, this chosen strategy provides a reliable path through the ambiguity of the problem, ensuring we achieve both efficiency and accuracy without over-relying on assumptions. To start, we need to clearly define the problem before diving into algorithm design. Here, we're tasked with finding the maximum sum subarray within a given array of integers. This means identifying a contiguous portion of the array that produces the largest sum. For example, in an array like -2, 1, -3, 4, -1, 2, 1, -5, 4, the subarray 4, -1, 2, 1 has the maximum sum of 6. The brute force approach to solving this problem involves systematically examining all possible subarrays. First, we iterate through every possible starting index of the subarray, and for each start index, we iterate through every possible ending index. For each combination of start and end indices, we calculate the sum of the subarray. This process ensures that all potential subarrays are considered, but as we'll see, it comes with significant computational overhead. As we continue with the brute force approach, we track the maximum sum found so far using a variable, max_sum, which is initialized to -infinity. During the iterations, whenever the sum of the current subarray exceeds the value of max_sum, we update it. Once all subarrays have been evaluated, the value stored in max_sum represents the largest sum possible. However, this method is highly inefficient. Generating all subarrays requires two nested loops, and calculating the sum of each subarray adds another layer of iteration. This results in a time complexity of n cubed, which is impractical for large arrays. To address this inefficiency, we turn to Cadon's algorithm, a more optimized approach. Instead of generating every subarray explicitly, Cadon's algorithm calculates the maximum sum in a single pass through the array. It does so by maintaining two key variables, max_so_far, which tracks the largest sum encountered, and current_sum, which represents the maximum sum of subarrays ending at the current index. In Cadon's algorithm, we process each element of the array sequentially. For the current element, we add its value to current_sum. If current_sum surpasses max_so_far, we update max_so_far to reflect this new maximum sum. However, if current_sum becomes negative at any point, we reset it to 0. This is because a negative sum would only reduce the potential maximum sum of any subsequent subarray. By the end of the iteration, max_so_far holds the maximum subarray sum. This approach is highly efficient, with a time complexity of n, as each element in the array is processed exactly once. This optimization makes Cadon's algorithm suitable for larger input sizes, where the brute force method would be prohibitively expensive. There are some critical insights to consider when comparing these approaches. First, the brute force method, despite being straightforward, is computationally infeasible for large arrays due to its cubic time complexity. Cadon's algorithm, on the other hand, is rooted in the idea that the maximum subarray sum ending at each index can be computed incrementally. If adding the current element results in a negative sum, the optimal choice is to start a new subarray from the next index. This eliminates unnecessary calculations and ensures efficiency. Additionally, Cadon's algorithm is space-optimized, requiring only two scalar variables, current_sum and max_so_far, to track intermediate results. This constant space usage, along with its linear time complexity, makes it a practical solution for this problem. When applying Cadon's algorithm, it's important to consider edge cases. For example, if the array contains all negative numbers, the algorithm will still find the least negative value as the maximum subarray sum, ensuring a meaningful result. For a single element array, the algorithm will simply return the value of the lone element. In the case of an empty array, handling this gracefully is crucial, with the algorithm either returning 0 or raising an appropriate error. To illustrate Cadon's algorithm in action, consider the array -2, 1, -3, 4, -1, 2, 1, -5, 4. Starting with max_so_far set to -infinity and current_sum to 0, we iterate through the array, updating the variables as we go. By the end, the maximum subarray sum, stored in max_so_far, is found to be 6, corresponding to the subarray 4, -1, 2, 1. This showcases the efficiency and effectiveness of Cadon's algorithm in solving this problem. The provided code solves an example computational problem that involves finding the maximum sum subarray within an array of integers, using Cadon's algorithm. The method unknown_problem takes a list of integers as input. First, it handles the edge case where the input list is empty, returning 0 as the result. The algorithm initializes two variables, max_sum and current_sum, both set to the first element of the input list. These variables will track the maximum sum found so far and the current subarray sum, respectively. The code then iterates through the array starting from the second element. For each element, it updates current_sum to be the maximum of the current element itself or the sum of current_sum and the current element. This step ensures that we either start a new subarray at the current element or continue the existing subarray. Next, max_sum is updated to reflect the maximum value between its current value and the updated current_sum, ensuring that we always have the largest sum encountered so far. Finally, the method returns max_sum, which represents the largest sum of any contiguous subarray within the input list. This implementation runs in O(n) time, making it efficient even for large input sizes. The simplicity of Cadon's algorithm ensures clarity and correctness in solving this example problem. This is the Java implementation of the given Python solution using the same logic. The problem is solved using Cadon's algorithm to find the maximum sum of a contiguous subarray. Key differences include explicit type declarations for variables, usage of Java's math.max method, and handling null arrays as an edge case. The logic is otherwise identical to the Python version, iterating once through the array to achieve O(n) time complexity. To solve problem number 1821, we start by analyzing the first example where the input array is nums equals 2, -1, 3, -4, 5. Initially, we set both max_sum and current_sum to the first element of the array, which is 2. This establishes our baseline. In the first iteration, we encounter the second element, -1. To update current_sum, we calculate the maximum between nums, 1, and the sum of current_sum and nums, 1. This gives us a result of 1. Since this new current_sum does not exceed the existing max_sum, we keep max_sum as 2. Moving to the second iteration, the third element, 3, is processed. Here, current_sum increases to 4 by taking the maximum of nums, 2, and current_sum plus nums, 2. This time, max_sum also updates to 4, as it is now the greater value. In the third iteration, we examine the fourth element, -4. The calculation for current_sum results in 0, as adding -4 to the previous current_sum of 4 does not yield a higher value than simply taking -4 on its own. The max_sum remains unchanged at 4 because it is still the maximum value encountered. Finally, in the fourth iteration, we process the last element, 5. Here, current_sum is updated to 5, as adding 5 to the previous current_sum of 0 exceeds taking 5 alone. Consequently, max_sum also updates to 5, which becomes the final output for this example. The maximum subarray sum in this case is 5. Now, we move to the second example where the input array is nums equals -3, -2, -1, -4. Both max_sum and current_sum are initialized to the first element, -3. In the first iteration, the second element, -2, is evaluated. For current_sum, we calculate the maximum between nums, 1, and current_sum plus nums, 1, resulting in -2. This also updates max_sum to -2, as it is now the higher value. In the second iteration, we encounter the third element, -1. Here, current underscore sum updates to -1, which is greater than the sum of the previous current underscore sum and nums, 2. Similarly, max underscore sum is updated to -1, as it is the new maximum value. In the third and final iteration of this example, we process the last element, -4. The calculation for current underscore sum results in -4, as adding -4 to the previous current underscore sum of -1 does not yield a higher value than taking -4 alone. The max underscore sum remains unchanged at -1, as no larger sum was found during this iteration. Therefore, the final output for this example is -1, which represents the maximum subarray sum for the given array of all negative numbers. Finally, we consider the third example with the input array nums equals 1, 2, 3, 4, 5. Both max underscore sum and current underscore sum are initialized to the first element, 1. In the first iteration, we evaluate the second element, 2. Adding 2 to the previous current underscore sum of 1 gives a higher value than taking 2 alone, so current underscore sum is updated to 3. This also updates max underscore sum to 3. In the second iteration, the third element, 3, is processed. Here, current underscore sum increases to 6, and max underscore sum is updated accordingly to 6. In the third iteration, we process the fourth element, 4. Adding 4 to the previous current underscore sum results in 10, which becomes the new max underscore sum. Finally, in the fourth iteration, the last element, 5, is evaluated. Adding 5 to the previous current underscore sum of 10 gives 15, which updates both current underscore sum and max underscore sum. The final output for this example is 15, representing the maximum subarray sum when all elements are positive. The time complexity of this algorithm is primarily determined by the operations it performs to find the maximum sum subarray. First, there's a quick edge case check to see if the input array is empty, which takes constant time, 1. Then, during initialization, the algorithm sets up two variables, max underscore sum and current underscore sum, both of which are assigned the value of the first element in the array. This setup step is also a constant time operation, 1. The main computational work happens in the iterative step. Here, we loop through the rest of the array, starting at index 1 and going up to the last element. For each element, we update current underscore sum by taking the maximum of the current element itself or the sum of current underscore sum and the current element. This ensures that we are always considering the best subarray sum that ends at the current position. After updating current underscore sum, we check whether it's greater than max underscore sum and update max underscore sum if needed. Both of these operations, updating current underscore sum and max underscore sum, are constant time, 1. Since the loop runs 4 n1 iterations where n is the size of the array, and each iteration involves only constant time work, the overall time complexity for the loop is n. Combining this with the earlier constant time steps, the total time complexity of the algorithm is n. When we look at space complexity, this algorithm is highly efficient. The input array nums is passed into the function but is not modified or duplicated, so no additional space is used for input storage. The only extra memory utilized is for the two scalar variables, max underscore sum and current underscore sum. These variables require constant space, 1, regardless of the size of the input array. Importantly, the algorithm does not rely on any additional data structures such as arrays, lists, or hash maps, which keeps the space usage minimal. Therefore, the overall space complexity of the algorithm is 1, making it optimal in terms of memory usage as well as computational efficiency. Now let's compare this approach with a brute force solution. The brute force method involves generating all possible subarrays of the input array, which are n squared, in total for an array of size n. Calculating the sum of each subarray adds an additional n complexity in the worst case. This results in an overall time complexity of n cubed, which is far less efficient than Cadan's algorithm. In contrast, Cadan's algorithm achieves the same result by traversing the array just once and using running sums to keep track of the maximum subarray sum. This reduces the time complexity to n, making it an optimal linear time solution. Despite these differences in time complexity, both approaches share the same space complexity of 1, since neither uses extra data structures. Looking at best, worst, and average case scenarios, Cadan's algorithm performs consistently in n time. Whether the array contains all positive numbers, all negative numbers, or a mix of both, the algorithm always processes the entire array in a single pass, maintaining its linear time complexity in every scenario. To mathematically understand why the time complexity is O(n), consider that the algorithm processes each element of the array exactly once after the initial setup. For each element, it performs one comparison to calculate current_sum and another to possibly update max_sum. Both of these operations are O(1), and since there are n1 elements after the first, the total number of operations is proportional to the size of the input, n. This eliminates any higher order terms or nested operations, confirming that the time complexity is O(n). Additionally, the space complexity is O(1), because the algorithm uses only a fixed amount of memory, regardless of the size of the input. No extra memory is allocated for data structures or recursive calls, and the only memory overhead comes from the two scalar variables. This makes the algorithm both time and space efficient, particularly well suited for large input arrays. Common mistakes in problem solving often stem from a lack of clarity or preparation. Misunderstanding the problem statement is a frequent issue, and this typically happens when you jump into coding without fully grasping the constraints or edge cases. To address this, take time to clarify any ambiguous details with the interviewer and confirm your understanding by reviewing input-output examples. Another pitfall is ignoring edge cases, which can occur when you focus solely on the happy path, common scenarios where everything works smoothly. To prevent this, explicitly list out edge cases before you start coding and ensure you test them thoroughly after implementation. Overcomplicating the solution is another challenge, as it's easy to get tempted to use advanced algorithms or data structures when a simpler approach might suffice. Begin with a brute force solution to establish a baseline, and then optimize iteratively. Finally, neglecting time and space complexity can lead to inefficient solutions that fail for large inputs. Be proactive by analyzing the complexity of your approach during the design phase and identify any potential bottlenecks early on. Incomplete testing is another common mistake, and it often happens when you rely solely on the examples provided in the problem statement. These examples are rarely comprehensive, so it's important to create your own test cases. Include edge cases and stress tests with large inputs to ensure your solution is robust. Now, in interviews, understanding patterns is key. Many problems fall into recognizable categories, such as sliding window, dynamic programming, or graph traversal. Recognizing these patterns can significantly simplify your approach. Also, always explain your thought process as you work through the problem. This shows your problem-solving skills, even if your solution isn't perfect. Time management is critical. Allocate about 10 to 15 minutes for analyzing the problem and 30 to 40 minutes for implementation and testing. Avoid getting stuck on one part of the problem for too long. Additionally, iterative optimization is highly valued. Start with a brute force solution and improve it step by step. Lastly, don't hesitate to ask clarifying questions early if any part of the problem is ambiguous. This will save time and help avoid unnecessary mistakes. To solidify your understanding and practice effectively, it helps to explore related problems. For instance, toSum, which is LeetCode problem 1, focuses on hashing and efficient lookups, making it a great exercise for mastering hash maps. The longest substring without repeating characters, LeetCode problem 3, centers on the sliding window technique and hash sets, which are essential for problems involving substring or subarray analysis. Merge intervals, LeetCode problem 56, emphasizes sorting and interval merging, skills that are useful in a variety of scheduling and range-related problems. Lastly, binary tree maximum path sum, LeetCode problem 124, combines recursive tree traversal with dynamic programming, offering a deep dive into handling recursive problems efficiently. Working through these problems will strengthen your ability to recognize patterns and apply the right techniques in different contexts. When it comes to tackling problems, there are several approaches to consider, each with its own trade-offs. Brute force is the simplest to implement and is often a good starting point to validate correctness. However, it's typically inefficient for large inputs, so it's not suitable as a final solution. Optimized approaches, on the other hand, require a deeper understanding of advanced data structures like heaps or hash maps. While these can significantly improve efficiency, they often demand more effort to design and implement. Divide and conquer is another powerful technique, especially for recursive problems like the maximum subarray sum. While it can simplify complex problems conceptually, it may introduce additional complexity in implementation. Finally, dynamic programming is invaluable for problems with overlapping subproblems. It's highly efficient but requires careful planning to define the state and transitions correctly. Understanding when and how to use these approaches is essential for crafting effective and efficient solutions. Great job following along. In this session, we addressed a unique problem and emphasized strategies for handling ambiguity. Remember to stay methodical, clarify assumptions, and practice tackling unclear challenges to build problem-solving confidence. Thanks for watching, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!